Assalamualaikum and hi, we continue on second part of the frequency response design via lag compensator. So this is the drawing of the lag compensator on the dot plot of the magnitude part. So this is the low cutoff frequency, where this is actually equal to pole compensator of the lag compensator, and this is the high cutoff frequency, which is equal to zero compensator of the lag compensator, and between these two frequency, low and high frequency, we draw the negative 20 dB slope to determine this part. The crossing point between the slope and the 0 dB is actually the low cutoff frequency and PC value, the pole compensator. So this is the transfer function of the lag compensator, S plus ZC, where ZC is equal to this one, and S plus 1 over alpha T, where this one is actually PC, the pole compensator, where alpha is larger than 1. So for example, we have this transfer function, open loop transfer function. Usually in the question, instead of giving the value of unknown gain K, the question will give you based on the steady state error information. In this case, velocity error constant KV, since this is type 1. So in this case, you have to use KV equal to 10 to determine this unknown gain K. That's why the first step is determine K from steady state error requirement. The velocity error constant, in this case KV equal to 10, is the steady state error requirement. And then once you determine this K, okay, KV is equal to this formula and then equal to 10, and then we calculate K new equal to 10, and then by knowing the value of unknown gain K, which is 10, we construct the Bott table from G, J, omega, meaning that we need to replace S with J omega. Okay, so based on this one, we construct the Bott table, and based on the Bott table, we draw the Bott plot. So this is the Bott plot. For this one, this is just a handwritten sketch. It's not really accurate, but this is good enough for explaining based on the theory and from step 1 until step 8. Okay, so this is the magnitude plot and this is the phase plot. Okay, so step 2, usually given in the question is percent of overshoot. So we determine the zeta or the damping ratio from this percent of overshoot, where the formula is provided in the lecture notes in frequency response design via gain adjustment. The next one, based on this one, the next one we determine the desired phase margin, dPm. Okay, but this one actually the question gives you the desired phase margin. Okay, phase margin to be at least 45 degree. Use the lag compensator, a correction factor of 10 degree. So please remember that the correction factor is usually between 5 to 12 degree given in the question. Okay, so based on the desired phase margin 45, or otherwise we can determine the desired phase margin from the value of damping ratio based on the formula of phase required phase. And then we should consider the corrected desired phase margin based on the correction factor. And finally, we determine the phase margin based on the corrected dPm using this formula. Okay, and then based on this value, we determine the frequency of phase margin. We label as omega Pm prime. At omega Pm prime, the value of phase plot is phi m. Let's say this value is negative 120. So from phase plot at negative 120 degree, you determine what is the frequency that we label as omega Pm prime. So at negative 180 and negative 120 degree, we determine what is the frequency and label as omega Pm prime. Okay, that's it for step number 2. We continue the next 2 steps in the next video. Thank you.